Eventually today we're going to look at shapes of molecules. So a student many years ago said to me, since we can't see molecules, why do we care about their shape? And I was just like, why is the mountaineer climb the mountain? Because it's there. All right, so if we can ask the question, we want to find the answer. So in Lewis theory, the valence electrons of a main group element are represented as dots around the symbol of the element. And so hopefully you can tell me from looking at the periodic table how many valence electrons a given element might have. And it says here for any main group element except lithium or helium and hydrogen. Hydrogen has how many valence electrons? Yeah, 1, and helium has 2. So for the most part, the number of valence electrons is equal to the group number of that element. That would be those Roman numerals on that periodic table over there. So when I look up at oxygen, I see Roman numeral number 6, and then I tend to like to go like this: 1, 2, 3, 4, 5, 6. And I almost imagine 4 orbitals around the 4 sides of the square. And it really doesn't matter how you do it. This is just as valid. Sometimes it's nice to do it this way. And we'll talk about Hund's rule in a second with how we put the dots around an element. So here is the Lewis dot symbol for oxygen. It has 6 valence electrons, and we use a dot for each one there. So I just commented here on number 2. The exact location of the dots is not critical. We fill the dots in singly first and then pair them up, with the exception of helium. And I kind of think about that being like Hund's rule. Anybody knock out the homework yet? So that second row of the periodic table is probably the one we look at the most. So here's oxygen. Look up, see Roman numeral 5, see nitrogen, 4 above carbon, lithium, alkali metal in that first column. And so we can easily see the number of valence electrons. More importantly to me is if I imagine 8 around each one of these symbols, it can tell me something about bonding or maybe charge. Atoms with 8 valence electrons, which are particularly stable, are easily identified because they have 8 dots as an octet. So we'll talk about the octet rule. Write the Lewis structure for phosphorus. I'm going to look up at the periodic table. There it is, Roman numeral number 5. I like to do some Hund's rule there. Stick that one in. And that should do it. We're going to have to skip over that because that wasn't right. That looked like oxygen. And maybe that's the beauty of Lewis structures. Helium's an exception. We don't like go around the atom. We just put them all on one side. And we say it contains a duet pair. And that's the most stable configuration because we filled up the 1s orbital, and that's what nature likes. All right, now we get to kind of go back to the beginning of the semester when we talked about nomenclature and the classification of different compounds. We have ionic compounds and molecular compounds. Of course, we used formula units for our ionic compounds, and we're going to talk about the different types of bonds. Covalent bonds we associate with molecular compounds. Ionic bonds we associate with ionic compounds. What's the difference? How can you immediately tell me if a compound is ionic? Yeah, metal and a non-metal. So covalent things, you're just going to see non-metals like sulfur and oxygen. So electrons are transferred in ionic compounds. Here's the Lewis structure for potassium. Here's the Lewis structure for chlorine. Potassium really wants to give up an electron, and it can go right there. So here you see a chlorine. It has 2, 4, 6, 8. So it has a full valence shell of electrons. It's happy. Now potassium, if I did the electron configuration, I would probably do something like this. And so this thing here is isoelectronic with argon. It gave up its valence electron. So it now has a full octet in the layer underneath this one, and hence the positive charge and the negative charge. So it's that electrostatic attraction that bonds these two elements together, and we call that an ionic bond. And there's no sharing of electrons. Chlorine has hogged them all. Potassium got rid of its. So I do this one more time here. Just go up a row to sodium. There's its Lewis structure, 1 valence electron, There's where it's at. It's in the 3s orbital. And that goes away. It looks like this. So here's chlorine. Here's its electron configuration, and notice it's one shy in the p orbital set. I can put 6 in there, so I go ahead and do that. And there, this is now isoelectronic with argon once again. And so we can imagine this positive charge and this negative charge, that electrostatic force holding these together. And this is the simplest ratio of these two, and we write NaCl. And you've seen the graphics where I have a 3D cube of this, and you see that the whole crystal lattice is alternating positive and negative charges. In Lewis theory, a chemical bond involves the sharing or transfer of electrons to obtain a stable electron configuration for each atom involved in the bonding. So far we've mainly looked at ionic. If the electrons are transferred, the bond is an ionic. If the electrons are shared, the bond is a covalent bond. In either case, the species involved obtain a stable electron configuration. Metals like to give up electrons to do it. Non-metals like to take on electrons, and that's easily seen in ionic compounds and substances. So here, now we see more of the crystal lattice. And sometimes I tell students electrostatic charge is kind of like magnets. And you could actually stack magnets up like this. So here's a south pole, and it's surrounded by these north poles. Here's the north pole, it's surrounded by the south pole. And then we can also do this out in a 3D arrangement. Crystal of table salt, and sodium's the much smaller species up there. All right, now what about covalent bonding? Covalent bond results when electrons are shared between two non-metal atoms. So we already discovered right at the beginning that ionic substances, a metal and non-metal, covalent bonds got to be non-metal atoms and to make a molecular compound. So here's our favorite molecule. So here's hydrogen, its Lewis dot structure. Here's another one. Here's oxygen's Lewis dot structure. So I made hydrogen's electrons red, and now you can see around oxygen I have 2, 4, 6, 8 electrons. So oxygen is now isoelectronic with neon. It's nice and stable. And the hydrogens are isoelectronic with helium, nice and stable. Now this doesn't represent a very good picture, because what do you know about hydrogen and oxygen as far as they exist as elements? They're diatomic. So I got my diatomic elements. And once again, I color-coded the electrons. And so now all the electrons are conserved, all the atoms are conserved. Life's pretty good right at the moment. So the octet rule states that when atoms bond, they're going to do it in such a way that each atom requires 8 electrons, with the exceptions of hydrogen and helium. So we used to have a 3s out here by sodium, and it went away. So now there's 8 electrons there. This chlorine here in the outer level, you see 8. This oxygen sees 8 around it. So here's our water again. And so when you come up with a structure, you sometimes make a circle and you say this hydrogen has 2, this hydrogen has 2, this oxygen has 8. Looks like a silly Venn diagram, doesn't it? So what they have in common is the covalent bond. The shared electrons, those that appear in the space between the two atoms, count towards the octet. Everything is satisfied here. All right, Lewis theory predicts the correct chemical formulas for ionic compounds. I could probably do this in a non-ionic way. We got sulfur, 6 electrons. Then I can imagine a sodium coming in like this and bonding up like that. And now I get to count my 8 electrons around sulfur. Here's how we really properly probably want to do it. And we learned this at the beginning, where if I said, what's the compound formed between sodium and sulfur? You looked up at the periodic table and decided that sodium's in the first column. You looked up and saw that sulfur's a non-metal and it's 2 columns away, or it has that number 6 above it, and you said 6 minus 8 is a -2. And once you got to that point, you said, oh, I need 2 of these, the least common multiple, and you wrote a formula like that. All good and great things here. Why do diatomic elements form molecules? I got a hydrogen and a hydrogen. And if those get together and share electrons, eventually we're going to see that where we see a pair of electrons, we can make a dashed line to represent a pair. So now I have a hydrogen bonded to a hydrogen. Oxygen, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I flip that one the other way around, and now I can draw in this oxygen. And let me ask you a question. Does each oxygen have 8 electrons around it presently? 2, 4, 6, 7. 2, 4, 6, 7. That's not good. So watch this. If I erase that dot, put it there, erase that dot, and put it there. Now maybe I can make one that looks a little more symmetric. Whoops. It's trying to get ozone there for a second. So we see that oxygen has a double bond. And this is what Lewis theory predicts. What about 2 nitrogens? Look up at the periodic table, you get 5 electrons. All right, well, if I have 5 electrons and I got 2 atoms, I'm gonna start getting a little more sophisticated here. I just burned up 8. I got 2 electrons left. I might as well put them over here, right? All right, so I should have 2, 4, 6, 8, 10 electrons. This nitrogen's nice and happy. It has an octet. This nitrogen here only has 4 electrons around it. So that means I need to move that pair in and maybe move that pair in. So eventually I get something that looks like, in that circle thing we looked at, I get to count 8 electrons around this nitrogen, 2, 4, 6, 8. And I get to count 8 electrons around this nitrogen, 2, 4, 6, 8. And there's 6 electrons between them, making 3 bonds. We say nitrogen is triple bonded. Chlorine, look up and you'll count to number 7, Roman numeral number 7 around there. So 2 chlorines, 7 valence electrons. How many electrons should I have? 14. Do I have them all? 2, 4, 6, 8, 10, 12, 14. Any questions about this process? So you probably just saw me illustrate what's on this slide. When 2 electron pairs are shared between the atoms, the resulting bond is a double bond. 2 pairs, that means 4. Double bonds are shorter and stronger than single bonds. The distance between 2 oxygen nuclei and an oxygen-oxygen double bond is 121 picometers. In a single bond, it's 148 picometers. Anybody remember pico? 10 to the negative 12th. So Lewis theory does correctly predict the double bond for oxygen. If you have liquid oxygen, you can catch it between 2 poles of a magnet. We say it's paramagnetic. So I'll put in a plug-in for general chemistry. Take general chemistry and you can find out what that means. So thus far you've seen me do some very simple Lewis structures for diatomic elements. Not too exciting there. So generally the first step is you figure out how many valence electrons you have to work with. Should be an even number. Divide the total number of valence electrons by 2 to find the number of electron pairs in the molecule. Surround the central atom with 4 electron pairs, then move the other remaining atoms around the central atom. Then you use the remaining electron pairs to complete an octet around the other atoms. If there are not enough electron pairs provided to make an octet for each atom, and you saw me do this, I moved non-bonding pairs between 2 atoms that already share an electron pair. There's this thing called valence shell electron pair repulsion. Like charges repel each other. So we have these electrons that make up bonds. They're negatively charged. They're going to be repelled by other bonding groups. And they're also repelled by lone pairs. Lone pairs, double bonds, single bonds, triple bonds, they all repel each other. And this repulsion between the negative charges of the electron groups on the central atom, or sometimes we say domains, determines the geometry of the molecule. Why do we care about the geometry of a molecule even though we can't see them with our eyes? Because the shape might dictate things like polarity, solubility, melting point. In a lot of biological sense, there's a lock and key model of how things interact. Write the Lewis structure for carbon dioxide and predict the shape. What's our first step? I look up at the periodic table and I get 4. I got 2 oxygens and I get 6. So I'm summing up all my valence electrons. 12, and 4 should be 16 electrons. That should give me 8 electron pairs. All right, what do I do with my 8 pairs? Well, maybe off to the side, I might try and convince you something like this. There's these empty holes around those elements. And we see that carbon likes to form 4 bonds, oxygen likes to form 2 due to their valence structure. So the whole point of that discussion is I'm probably going to choose carbon to be my central atom. And a lot of times the central atom is given first, not always. Surround the central atom with 4 pairs. That gives me 4 pairs left over. Then typically you move in your other 2 atoms there. And I use these 4 pairs to do what? Complete octets. So I'm going to go 1 pair, 2 pair, 3 pair, and 4 pairs. Now when I look at this carbon, I say it's happy. There's 8 electrons. When I look at this oxygen, I say, I get 2, 4, 6. Same thing going on there. So that previous slides, when it says when you don't have enough pairs to complete octets, it says move a non-bonding pair between 2 atoms that are already sharing a pair. So that means I move that pair down there and that pair down there. Now I get to count 8 electrons there, 8 electrons there. Each oxygen has an octet and that carbon has an octet. Does this look like a reasonable structure as far as the shape goes? What did you just learn? These things are kind of close together. They want to be as far apart as possible. All right, so this electron domain and that, and what do you say when 2 people are far as apart as possible? Polar opposites, they're 180 degrees apart, and that tells us quite a bit there. And what do you suppose this is? Right, carbon dioxide, it's got the double bonds and everything. I knew this was going to happen. Now, they got the colors right, but they failed to do their double bonds that correctly. So this is a linear shape, has a bond angle of 180 degrees. Write the Lewis structure for H2O. All right, what am I doing there? Summing up the valence electrons. How many pairs do I have? So do I want to put those 4 pairs around the first hydrogen? You know, when I first taught this class, students would do something like this sometimes. There's my structure for water. And I'd look at that. Well, presently I see 2 4 electrons around that hydrogen. Hydrogen can only have 2. So I said generally the central atom is given first, but not always. And we learned that oxygen likes to form 2 bonds because it has 6 valence electrons and can take 2 more on. It kind of makes sense to, there's our 4 pairs. And then of course I like to hook up my hydrogens like that. And you've seen me write water like that quite a bit. There's my show and tell. And looky here, this is how water's depicted. The red spheres, which represent oxygen, only have 2 holes in them. So today in lab, when you play with these, and Thursday morning, I'll say if you build a model and there's holes in one of your spheres, there's probably a problem. Now notice there's these lone pairs, and this is a near and dear shape to chemists. It's called a tetrahedral shape, or a tetrahedron. There we go. So at the points of this tetrahedral, I got bonding groups, 2 hydrogens there, and here I have the lone pair. So all these electron domains want to get as far apart from one another, and that's why we get this shape. Any questions on the Lewis structure for water? So right off the beginning, I'll do my comedy. Of course, we don't want to do this. This is the student who just does not care. Done, I get a hand in my lab. Lots of trouble with that. Before we start there, let's go ahead and actually, normally it's typed out this way. This is how I would normally type it out. 4 electrons from carbon, Roman numeral number 4 up there. I have 2 hydrogens at 1 each, oxygens at 6. So looks like 12 electrons, 6 electron pairs. When I look at all these atoms, hydrogen can only form 1 bond, oxygen likes to form 2 bonds, carbon likes to bond 4 times. Makes sense to make carbon my central atom. All right, I just burned up 4 pairs. That's how many pairs I have left. All right, then I move in the other atoms. A hydrogen, an oxygen. These 2 pairs left. I'm gonna try and complete an octet. Does that oxygen have an octet around it? No, so I'm gonna take these and move those down. Now when I look at this, I get a count 2, 4, 6, 8 around that oxygen. I get a count 2, 4, 6, 8 around that oxygen, 2 around that hydrogen, 2 around that hydrogen. So that was a nice structure before I gummed it all up with my Venn diagram. And here's the model. And we see a double bond between oxygen and carbon. There's the 2 pairs of electrons. That's our double bond. And we even see this shape. It's flat and planar and maybe looks like a equilateral triangle, or if I put this in a circle, what symbol would it make? Like a peace sign or your Mercedes-Benz. So we get to predict flat and planar, 120-degree bond angle. What's a bond angle? It's an angle prescribed between a central atom and 2 other atoms. The carbon dioxide was 180. What's the name of this? Ammonia. Close. What's the first thing we want to do? All right, how many do we have? Perfect 8, I think. 5 and 3 hydrogens at 1. 3 and 5 sum up to 8. So wherever I see a pair of electrons, I get a draw a dashed line. What's the shape of this? Notice I was a little artsy here. It is what we call trigonal pyramidal in structure. So here's the model. And some woodworker cut these, and for some reason these light blue spheres he put on a lathe, and there's a hole that goes right through them. And so I took a bunch of these and I took that rock wood putty stuff and plugged them up. So notice they're trying to show you here we still have the tetrahedron shape, and at each point we either have a atom or a lone pair of electrons, and that's why we get this pyramidal shape. What's CH4? Methane, natural gas. It's going to look like this. So, of course, let's just do this. 4 electrons from carbon, 4 hydrogens at 1 each, 8 electron, 4 pairs, and there it is. So it's a perfect tetrahedral shape, 109.5 bond angle everywhere. So we did the majority of these on this list. And so how do you know these shapes? I call this thing a truth table. Here I had 3 bonding domains, 3, and then I have 3 bonding groups and 0 lone pairs. That gives me the trigonal planar 120. You can see this isn't drawn very well here, but that's that. When I do carbon dioxide, I see 2 electron groups. Domains also works nicely. 2 of those are used in bonding. 0 non-pairs, so this thing's linear. Let's do the ammonia. You're going to have 4 electrons all around that. 3 are used for bonding. 1 is not used for bonding, and you get this shape. And as they say over in England, get bent. All right, you'll get more use of this table in lab. I wanted to make it through the table before you got to lab.